Hello, good morning, class. Can you hear me from the other end? Hello, class. Can you hear me from the other end?
Yes.
Yes, sir.
We
Yes, sir.
can hear you, sir.
All
Yes.
right.
We can hear you, sir.
Yeah,
Can hear you, sir.
yes, we can
We
hear
can hear you,
you,
sir.
sir.
Yes, sir. We can hear you, sir.
Hallelujah,
The link I
sir.
sent.
We can hear you, sir.
Yeah,
We
can I
can
be?
hear you,
Yes,
sir.
sir.
Maybe,
We hear you.
sir.
Yes, sir. We can hear you, sir.
I can hear you, sir.
The link on the LMS.
I'm very much hear you, sir. Very well, sir.
Very much
Just
welcome,
speak.
sir. Highly welcome,
I can
sir.
hear you, sir. I can hear you.
Sir,
Thank
mute
you so
this
much.
class,
I can hear
sir.
you, sir.
I can hear you. Yes, sir.
We can hear you, sir.
Thank
All right. There's a link on the LMS page. For those who are unable to join this class, they can follow us on YouTube.
Good morning, sir.
All right. My name is Nathaniel Damiladojo, and I'll be taking you the other aspects of CH156. I'll be handling acid, bases, and salts aspects of the course. And under this course, broadly, we're going to look at acids, bases, pH, salts, and buffer solution. And buffer solution. These are the content of the course. Under the unit one of the course, we'll be looking at acid and bases in our environment. The unit two is about properties of the acids and bases. What are the properties? What are the features that we are looking for to make us to be able to say that this is an acid, maybe this is a base. So we're going to look at those properties. The unit three is about the concepts of the acid and base. How can we define acid? How can we define a base? So we're going to be looking at how Arrhenius defined acid and bases, how Brunellari defined them, and how Lewis defined acid and bases. What is the difference between how Arrhenius defined an acid and a base, and how Brunellari and Lewis defined the same concept? Unit 4 is about the strength of acids and bases. What makes us to be able to say that this is a strong acid, or maybe this is a strong base? What is the difference between a strong acid and a concentrated acid, or maybe a strong acid and a dilute acid? Is it the same thing, or is it different? Also, under this unit 4, we're looking at acid and base dissociation constants. Unit 5, we'll be looking at acid-base equilibria in aqueous solution. I'll also be considering the pH scale. Unit 6, we'll be looking at hydrolysis, how we can define and calculate the equilibrium constant, the pH and pOH of aqueous solution of salts. We'll also be looking at buffer solution. How can we define that? What is buffer action? How can we prepare a buffer solution? What do we use them for? How can we calculate the pH of buffer solution? And lastly, we'll be considering acid-base indicators. Acid-base indicators. So we'll be looking at acid-base strength and the chemical structure. The objectives of this part of the course is, by the end of this, You should be able to differentiate between an acid and a base using their definitions and properties. You should also be able to explain the concept of neutralization. What is neutralization? It may not be so strange from you. Some of you did a similar thing in secondary school. However, we'll be looking at the concepts together. Then you should also be able to solve some problems that relate to buffer action, pH of acids, bases, and buffer solutions. All these you're going to learn in the course of this study. So, into the course, we will be looking at acid and bases in our environment. There are acids in our environment, and some of you may be familiar with those acids. One of the examples is unripe fruits. Maybe you have a lime or maybe lemon. If you have a taste of it, some of you may not like to taste unripe fruits. Even if it is orange or mango, you may not like the taste because it is rich in acid. It is very, very rich in acid. You can see some pictures over here. You'll be able to see some pictures here where we have some fruits, maybe some vegetables, and even some medicine. So an acid, you can find it in our environment in sour milk. You may be talking about maybe lactic acid. You may find that one in sour milk. You may find some maybe ascorbic acid in fruits, or maybe citric acid in some citrus fruits. You may be able to see some citric acid. But you may be asking that, how will I know that what I'm tasting or what I'm interacting with is an acid? Later in this course, we'll be looking at the properties of an acid. What can make us say this is an acid, this is not an acid? So we'll check the properties, not now, but later in the course of this study. You may also be familiar with car batteries, especially those wet cells. They have electrolytes, which is also an acid. We'll be able to find concentrated solution of sulfuric acid, or maybe you call it tetraoxosulfate 6 acid, concentrated form inside the car battery. So acid are just everywhere. Even if you look at yourself as a human being, you also have acid in your body, especially in your stomach, because some digestive enzymes in your body need an acidic medium, especially the gastric juice. You need this dilute HCl, that's hydrochloric acid, for those enzymes to function properly. And they aid in activating the enzymes in the stomach for them to work on the food you have eaten to digest them properly. So even inside human body, we have stomach acid, that's gastric acid, like dilute HCl. If I ask you to carry out a lot of work over a stretched period of time, maybe 3 hours, 4 hours, 5 hours, you may discover that with time, the efficiency with which you started the work starts to reduce. And that is because fatigue or maybe stress, weakness starts setting in. You may start feeling some pains in your muscle, maybe some aches. That is as a result of some acids present, some acids released into your muscle. And an example of that is lactic acid. Lactic acid. So human beings, generally we have acids in our body, which gives us an idea of what you are doing. Are you overstressing yourself? Have you done it to the limit? Or some are very helpful, like the ones we have in our stomach, and can also be dangerous if the amount we have there is going beyond what is necessary. In the environment also, we may have some acids, for instance, in what we call acid rain. We may have some dissolved gases, dissolved acidic gases like SO2, CO2, NO2. When SO2, possibly in the presence of some energy up there, maybe light energy, interacts with atmospheric oxygen, we will be having this SO3 gas. We'll be having the SO3 gas. And if you have SO3 gas, this can interact with moisture in the atmosphere, and you can have H2SO4. That's tetrahydrosulfate 6 acid, which can be dissolved up there. And when it rains, it falls on the ground and can be absorbed by plants. It may move into water bodies, and some of us may even collect the rainwater and try to drink it. So we may introduce a lot of acid into our body unconsciously. Normally, this should be a dilute acid, but in some areas, it may be concentrated. So we may have SO2 or maybe CO2 or NO2 in the atmosphere dissolving in the rainwater and falling down on the ground. And this can add to the acidity of the soil. Okay. Likewise, we may have bases in the environment. Apart from the acids, we may have different bases. An example of that may be this that is called milk of magnesia. Possibly sometimes ago, someone may be complaining of stomach upset. Maybe the stomach is not, you're not feeling very well in your stomach, and they may ask you to go and take maybe some brands like maybe mixed mag or maybe milk of magnesia or so. That is a form of a base. That's a form of a base which is able to neutralize or at least reduce the potency of stomach acid. And we have said that we have majorly dilute HCl in the stomach. We have dilute HCl in the stomach. So when you take this antacid, at times they call it antacid, that is a chemical reagent that may reduce the potency of an acid, possibly in the stomach. So when you take this antacid, it has a way of neutralizing or at least reducing the effectiveness of the stomach acidity, and then you may feel some relief if that is what is leading to the stomach upset. Likewise, in some cleaning agents, we may have some ammonia there, and that one can also aid in the cleaning effects of that cleansing agent. Bleach, some bleaches that you use, maybe hypo and all those bleaching, those bleaches, some of them, or even most of them, have bases in them. They have bases in them. So how do you know that they are bases? You'll see that when you touch maybe soap or maybe a detergent, you would observe that it has a different texture. So when you touch just water, maybe it is slippery. Possibly it is slippery, and in lower classes you might have been taught that bases have slippery, but bases are slippery to touch. So inside in those soap or maybe detergents, we have bases. All right. There is another chemical called lye. It is also rich in sodium hydroxide, and it's rich in concentrated form of sodium hydroxide, which is also a base. If a base is soluble in water, we refer to them as an alkali. So let's move on. And that is what we have under the unit 1 of this course. Under the unit 2, we'll be looking at the properties of acid and bases. We'll be looking at the physical properties. We'll also be looking at the chemical properties. How can you, without carrying out an experiment, how can you have an idea of whether what you have is an acid or a base? There are some ways in which you can test it without a major chemical experiment. So be looking at neutralization and some other properties. So the physical properties of an acid include sour taste. Sour taste. An acid may have a sour taste. Very, very poisonous. Very, very poisonous. So it will not be so easy to be tasting it. But how do we know that some acids have sour taste? Then maybe you have tasted, possibly you have tasted maybe lemon before, or maybe sour milk, possibly sour milk. If you actually taste this, you observe that it has a characteristic sour taste, and that is as a result of the presence of acid in it. The other physical property of an acid is concentrated form of acids are corrosive. They can actually burn. They can eat deep even into fleshy materials. So it's not advisable to be interacting with concentrated acids. It may be very, very corrosive. An example of that is maybe the acid you have in car battery. We have already said that in the car battery, we have concentrated H2SO4. So any acid in the concentrated form can be very, very dangerous. So as much as possible, just try and avoid that acid touching your skin or maybe touching your materials because it can be very, very destructive. Another property that we can be looking at is an acid should be able to turn a moist blue litmus paper red. If it has a blue litmus paper and then you dip it into a solution of an acid, the color will change. If it's a blue litmus paper, you observe that the color will start changing to red. The color will start changing to red. And that one can give you an idea that, okay, what I'm working with is an acid and not just water. Because sometimes an acid may be colorless. It just look like the water that you've been interacting with every day. Also, on what we call a pH scale, an acid has a pH of 0 to 6. pH basically less than 7, maybe 6, 6 point something, 0 point, from 0 to 6. If it is 0, it means it's possibly a concentrated, very concentrated acid. And that one may deal with maybe how far that acid ionizes, whether it's a strong acid or not. But basically, if you have a concentrated acid, then the pH may be tending towards maybe 0, maybe 1, 2, 3. So, and a dilute acid may have a pH of maybe around 4, 5, 6. Acids also, they are generally soluble in water, especially when you have acids that have a proton, maybe an ionizable hydrogen ion in it. We also will be looking at the chemical properties of an acid. The chemical properties of an acid. One of the chemical properties of an acid is an acid should be able to liberate hydrogen gas when it interacts with active metals. What are active metals? They are basically, when you check the periodic table, we have group 1, we have group 2. Well, take hydrogen out. Then you may have maybe lithium, you may have maybe sodium, maybe you have potassium, and so on in the group 1 in the periodic table. And in the group 2, possibly you have maybe magnesium, beryllium, maybe um, beryllium, magnesium, this strontium, and so on. These are metals with high electropositivity. And when you check the activity series, they are typically far above hydrogen ion in the activity series. So these metals can liberate, they can displace hydrogen gas out of a solution when they interact with an acid. So if you have, for example, if you have H, let's say you have HCl, possibly it reacts with maybe magnesium ribbon. This is a aqueous solution, that's hydrochloric acid. You may be able to observe the evolution of hydrogen gas. Be able to observe an evolution of hydrogen gas. And that one give you an idea that what your acid is interacting with is a highly electropositive metal. An acid also should be able to form salt with a base or maybe an alkali. I've already said that an alkali is a soluble base. So if the base is soluble in water, you can refer to it as an alkali. If that soluble base, for instance, let's say sodium hydroxide, this is a base. Reacts with, let's take HCl again as an example, hydrochloric acid. What you will observe is that you will form sodium chloride, which is the normal table salt we use at home. Though for this reaction, you may not actually try to get the sodium chloride. So you may have the sodium chloride in the solution and water molecules. So an acid reacting with a base will give you basically salt and water. Salt and water. This is called a neutralization reaction. Remember, I was saying initially that in case if the stomach acidity, maybe the acid in your stomach secretion is high, maybe you have not eaten properly, and the secretion is just high and it's affecting your stomach, you can take, maybe after you have done some medical consultation, maybe you are provided with an antacid, something that can reduce the efficiency of an acid, you may feel some relief because what is happening right inside your stomach is called a neutralization reaction. The antacid you've been given is neutralizing the stomach acid. And that is why you may feel better. So neutralization is when an acid reacts, with a base, and then you have salt and water formed. Another chemical property of an acid is an acid. The aqueous solution of an acid is a very good electric conductor, and that is because there are mobile ions when a protonated acid dissolves in water. There is a presence of mobile ions, and that is how it is easy for them to conduct electricity. Okay, let us look at the properties of the base. We'll first consider the physical properties before we move on to the chemical properties. If you remember that at times when you're taking your bath in the bathroom, you may observe that the soap you are holding with water in your hand keeps falling or keeps dropping. just slippery and it's not very easy to handle. That is because the soap has as part of its ingredient a base. Maybe they have used maybe CaOH2, or maybe they have used sodium hydroxide. This is a base. This is a base. So you may observe that a base will have slippery feeling, maybe slippery to touch. The other physical properties a base may have bitter taste. A base may have. Not everything that has a bitter taste is a base. But a base should have a bitter taste. That doesn't mean that you should start tasting anything you see on site. That can be very, very poisonous. So you don't just taste them. But how do the people know that a base has a bitter taste? Maybe someone has mistakenly tasted maybe a bar soap or something before, and then the person is able to record that, okay, this is the base, and then the bitter taste attached to it. Now, another critical property we'll be looking at is that just like concentrated acids are corrosive, concentrated bases are also corrosive. Concentrated bases are also corrosive. That is, if you have a concentrated, maybe caustic soda or maybe concentrated sodium hydroxide, if that falls on maybe a material, either a wooden material or a cloth material, we are not expecting it to fall on human flesh. It may burn that material as if it is attacked by fire. That is why we'll say it is corrosive. It can also lead to fast corrosion process of that material. So it's advisable to always avoid concentrated bases as well as we avoid concentrated acids. We also said initially that an acid, you can test an acid if you put a blue litmus paper there because it will turn the moist blue litmus paper red. If you also want to test for a base, just take a red litmus paper, moisten it. Let's say this is the base. Moisten the litmus paper, red litmus paper actually, and dip it inside the base. You observe that the red color of the litmus paper will change to blue. This is an experiment you may be able to carry out if you get to the lab, or maybe you buy a litmus paper and you start testing. You can start using it to test maybe the detergent, the soap bar, and all those things you have at home at random. You may be able to observe that the red color of the litmus paper will change to blue if that compound is a base. A base also is a good conductor of electricity, and the pH value is greater than 7. So the pH value of a base is maybe 8 to 14. As it approaches 14, it means that's a concentrated acid. And around the 8, if the pH is around the 8, it may be a weak acid. Bases that are very soluble in water, I've already said that we call those ones. Let me clear this part. Bases that are soluble in water, we call them alkaline. Examples of that are sodium hydroxide and potassium hydroxide. Okay, so we can look at the chemical properties of a base or maybe an alkaline. One of the chemical properties is we have already said that an acid reacts with a base to form salt and water only, and that's the neutralization reaction. So we can take it as a base can interact with an acid to give us salt and water. That is a neutralization reaction. We have talked about it earlier. An alkali also should be able to react with an ammonium salt. Take, for instance, ammonium sulfate or ammonium tetroxysulfate 6. That's NH4 to SO4. So if we have The interaction of, let's say, this base, that's calcium hydroxide, with NH42SO4, in the presence of it, you may be able to observe that there will be evolution of ammonia gas. Ammonia has a bad smell. Maybe it smells like, maybe it has a choking, maybe pungent choking smell. If it gets inside water, it can even start tasting like maybe urine or so. So you may see evolution of this ammonia gas when the alkali or maybe the base react with ammonium salt. Ammonia gas is evolved. An alkali solution can also precipitate insoluble metal hydroxide. Take, for instance, if we have sodium hydroxide is soluble in water. We have said that because it's an alkali, it has a very good affinity for water. And if we have another salt, say copper 2 tetraoxosulfate 6, that's CuSO4, this sodium hydroxide is a solution. Say we have sodium hydroxide solution, and then we have CuSO4 solution. CuSO4. This is NaOH. If you mix these two solutions together, this is liquid, no solid inside. This CuSO4 also is liquid, no solid inside. But if you mix the two together, you observe that a solid particle will start forming at the bottom of the reaction vessel. And that solid particle is copper 2 hydroxide, that's CuOH2, while you have Na2SO4 still remaining in solution, because this is a sodium salt and it's very soluble in water. So an alkali can precipitate insoluble metal hydroxide, for instance, copper 2 hydroxide, from solution of a salt. This is a solution of copper 2 salt. And this is the insoluble metal hydroxide it forms. That's CuOH2. So all these properties are general properties of an alkali or a base, but there are some properties that are not general. For instance, the reaction of an alkali, especially sodium hydroxide with aluminium. Normally, most alkalis, maybe bases, don't liberate hydrogen gas, whether they interact with or whether they interact with a metal or so. They don't normally liberate hydrogen gas. But we have some cases in which sodium hydroxide, very strong alkali, can react with aluminium, maybe aluminium metal, or maybe you are able to get it into fine dust, and you have evolution of hydrogen gas. It's not a general reaction, just like I indicated here. So you can have this kind of reaction. So we have aluminum solid dropped inside sodium hydroxide solution, the presence of 6 moles of water, and then you have this sodium aluminate 3, with the evolution of hydrogen gas. It's not a general reaction, but that reaction does occur. And this is the end of the second unit of this course. So we can now move to the unit 3 of this course, the unit 3 of this section, which is acid, base, and salt. And in this section, we'll be defining an acid, we'll be defining a base, we'll be defining an acid, we'll be defining a base based on how Arrhenius, Brandt-Lowry, and Lewis, how they defined them. What is an acid according to Arrhenius? An acid is a substance that can produce hydrogen ions, or maybe you call it hydronium ions, or maybe hydrogenium ions, in aqueous solution. That is, if you dissolve that acid say maybe the acid is HA. If you dissolve it in water, just like what we have here, you observe that the hydrogen ion will be free in solution. But it won't just be like hydrogen ion in solution. It will exist as H3O plus. That's the hydronium ion in solution. And then you have the anion present in the solution. For instance, if you have maybe H, that's the proton, Cl, that's the anion part, dissolved in water, dissolved in H2O, dissolved in H2O, then you will have H3O plus, that's the hydronium ion, you can put aqueous here, plus the Cl, that's the chloride ion, Cl minus the chloride ion in solution. And this is characteristic of an acid that has an ionizable proton. That's why I wrote it down here that only hydrogen atoms involved in polar bonds are ionizable. So this should be a polar bond. Okay, let's take, for instance, let's take another example. Say we have CH3 COOH. Some of you, some years ago, you might have come across this particular chemical compound. You may call it maybe acetic acid, or maybe you call it ethanoic acid, depending on whether you are using the trivial name or you're using the higher name. So you can call it ethanoic acid. If you have this ethanoic acid, how many ionizable hydrogen ions do we have in this acid? You have CH3 COOH. You will observe that it's only this, just one ionizable hydrogen ion that we have in this compound, that's acetic acid. This implies that in solution, this acid can only release just one proton, just one hydrogen ion, just this. This other hydrogen ion, this H3, is not ionizable. It's not polar. So it cannot be ionized. And that may suggest that the basicity of this acid is 1. Basicity actually refers to the number of ionizable or maybe replaceable hydrogen ions you have in a compound, maybe an acid. So the basicity of this is just 1. Okay. So since we already know the definition of an acid according to Arrhenius, that an acid is a compound that can dissociate in water to give us hydrogen ions. We can now group Arrhenius acid into broadly 3. We can group it based on, does it have an oxygen, does it not have an oxygen? Does it have one ionizable proton? Does it have 2 ionizable protons? Or does it have 3 ionizable protons? If it has oxygen, maybe it's an oxy acid. An example of that is maybe HNO3. That's trioxonitrous 5 acid. You may also call it nitric acid. This acid has oxygen. So it's an example of oxy acid. It's an example of oxy acid. Another example is H2SO4. That's also an oxy acid. You can also have H3PO4. It's also an oxy acid. We may also have non-oxygen acids. An example of that is hydrochloric acid. Hydrochloric acid only has hydrogen atom and chlorine atom. There's no oxygen there. Yet it's an acid. So that is a non-oxygen acid. A a non-oxygen acid. So you can have hydrochloric acid, you can have hydrobromic acid, you can have HI, hydroiodic acid. These HBr, HCl, HI, they are non-hydrogen, not non-oxygen acids. That is, they are acids, but they don't have oxygen atoms. Okay. Then let's look at monoprotic acids. Monoprotic acids have one ionizable hydrogen ion. Let me take this hypothetical case. Maybe we'll have HA, for instance, dissolving in water to give us this hydrogen ion and this anion. If this acid releases just one proton in solution, it implies that this acid is monoprotic. This acid is monoprotic. It has just one ionizable hydrogen ion. I hope you are following. But what if we have, okay, an example of that is HCl. HCl, it can be, you may dissolve it in solution, and that one can give us H plus, it's a monoprotic acid, plus Cl minus aqueous. Another example is HNO3. HNO3 is, if you want to classify this, this is an oxy acid, but it's also a monoprotic acid. HCl is a non-oxygen acid, but it's also a monoprotic acid. We can have HNO3 as an example of a monoprotic acid. Let me clean this interface. Okay, let's talk about diaprotic acid. I know by now you'll have started thinking of, okay, an acid has been mentioned previously, H2SO4. Personally, this is a diaprotic acid. You are very correct. H2SO4 is a diaprotic acid because it has two ionizable hydrogen ions, two replaceable hydrogen ions. So H2SO4 is, if it ionizes in water, gives you two molecules of hydrogen ion plus SO4, that is a anion, 2 minus. Then we can have what we call a triprotic acid. A triprotic acid, just as the name implies, it has three ionizable hydrogen ions. And when ionized in solution, it releases the three ionizable hydrogen ions. They may not be so common, but an example of that is H3PO4. You can call it phosphoric acid or tetraxophosphate 5 acid. If this ionizes in solution, then you have three moles of hydrogen ion released with PO4 3 minus as the anion. It may be releasing it stepwise. However, it will be able to release all the three protons it has. And that's an example of a triprotic acid. By now, you may start maybe brainstorming on, do we have more examples about it? Yes, we do. So you may also find it comfortable or maybe convenient to read more text. If you go to the LMS page, there are some textbooks we've been able to put there for you as links, as web links. So when you click them, you should be able to download them into your devices, either your laptop or maybe your phone, your Android, your tablet, or anything. You're able to download them there. Okay, just before we move on, let's briefly look at strong and weak acid. What is a strong acid? A strong acid is an acid that can be completely dissociated in water. An acid that can completely dissociate in water. Take, for instance, HNO3. This is trioxonitric 5 acid. In solution, this acid releases all its hydrogen ions. So all the hydrogen ions are well dissociated, and you have the NO3 ion also there, which is the anion. So you have the H plus completely dissociated. So any acid that can completely release its hydrogen ion in solution is called a strong acid. The strong acid. However, we have what we call weak acids. They cannot release all the hydrogen ions in solution. And examples of that are organic acids. Basically, organic acids are weak acids. An example of that is maybe methanoic acid, or maybe ethanoic acid. Methanoic acid is HCOOH. That's methanoic acid. In solution, this should release just one proton. And also, we have this anion. That's the methanoic ion. So we have this H plus, but this H plus is not completely dissociated in solution. And later on, maybe later as we're going on, we'll be talking about dissociation constant. We're talking about that, and you will get to understand this concept better as we move on. So an acid that cannot release all its ionizable hydrogen ions in solution, we call those ones weak acids. It may be concentrated, it may be dilute, but that one does not affect the number of moles of hydrogen ions is able to release in solution. Okay. Let's take a step further. So we have already given examples of non-oxygen. We have the hydrogen, see that's HCN. We have the hydroiodic acid, that's HI. We have the hydrochloric acid, those ones are non-oxygenous acids. You may just want to copy them down, but you already have them on the lecture slides, and that has been uploaded on your LMS page. And then we have the oxy acids. Okay, we have mentioned H2SO4. We can also have this perchloric acid, that's HClO4. Is a very strong acid, very strong acid, HClO4. And we can have this H3PO4 as an oxy acid. We have already mentioned that. Okay, examples of strong acids. Okay, we have already said that HClO4 is a strong acid, HNO3 is a strong acid, HCl is a strong acid because they can fully release the hydrogen ions in solution. H-high, H2SO4, those are strong acids. But we can have weak acids like HF, H2S, H3PO4, HCN, and even we can have those organic acids. We have mentioned some of them like the methanoic acid, even lactic acid, ascorbic acid, ethanoic acid. Those are organic acids and they are generally weak acids. So in case if you are asked to mention maybe 3 weak acids, or maybe you have options that the following are strong acids, except that maybe they mention HClO4, HNO3, HCl, and then you have HCOH as part of the option, then you know what to choose. All right. We have already stated what we mean by monoprotic, diprotic, and triprotic acid. But you should note that, try and note very well that this AQ sign that we have up there means acid is dissolved in water and it forms an aqueous solution. an aqueous solution. Okay, let us look at Arrhenius' theory of a base. How did Arrhenius define a base? Just very briefly, we'll look at that. Just very briefly, we'll look at that. So Arrhenius defined a base as a compound that can release hydroxide ions in solution. That is, if you take the base and you put it in water or you put it into solution, it should be able to release the hydroxide ions. That is the definition of Arrhenius concerning the bases. We have mentioned some bases today, and an example of that is sodium hydroxide. So a base should be able to dissociate in water to release the hydroxide ion. That's the negative ion in solution. And then you have the sodium ion. So this characterizes a base, OH minus, according to Arrhenius. Strong bases completely ionizes in water, just like strong acids also completely ionize in water. And an example is what has been stated in this equation, NaOH aqueous, giving us Na plus OH minus. Weak Arrhenius basis partially ionizes in water, and AlOH3 is an example of a weak Arrhenius base. NaOH is an example of a strong Arrhenius base. But if you consider it very well, the definition of Arrhenius on acids and bases is restricted to aqueous solutions. What if it is not in solution? Is it still an acid? If I take it out, if I take hydrogen chloride out, if I take hydrogen chloride gas out of hydrochloric acid, has it lost its acidity? Is it still not an acid? So we will need to expand the definition of an acid and basis, and that is how Bronsted-Lowry definition comes in. Bronsted-Lowry definition of acids and bases. So, because of the time, in the next class, we'll be looking at Bronsted-Lowry definition of acid and a base. How did Bronsted-Lowry define an acid? Basically, it defined an acid as a proton donor and a base as a proton acceptor. So, referring to a proton, it means it may be in solution or it may not be in solution. So, Bronsted-Lowry definition of an acid and a base covers Arrhenius' definition of an acid and a base, and also goes beyond that into when the acid and the base are not in solution. For instance, if you have NH3, if it is NH3 solution, that's typically an Arrhenius base, but you can have ammonia gas. What if you have ammonia gas reacting with hydrogen chloride gas? Ammonia gas reacting with hydrogen chloride gas, it still forms a salt. It still forms a salt. So this acid, HCl gas, is able to donate its proton to the ammonia gas, and the ammonia gas is able to accept the proton. Remember we said a base is a proton acceptor. So it forms this NH4, that's an ammonium chloride salt, and that qualifies this HCl gas as a Bronsted-Lowry acid and NH3 gas as a Bronsted-Lowry base. All right, there is a link on the LMS page for you. There is a short quiz for you. The quiz is not your general continuous assessment. The quiz is not your general continuous assessment. It's just to see how you are following this class. So just go there and respond to it if you have not done that. The link will be available till tonight, till around 11:59 p.m. today. So just access the link. It's already on the LMS page. Access the link and try and solve the quiz question. If you have questions also, maybe you can put it in the chat section. And we'll be stopping here for today. Okay. So I may need to log out. If you have a question, you can just put your question in the chat section. We'll be able to access it and attend to them. And if you have a challenge with the link to the quiz, we'll also work on that.